Welcome back, children. In the previous videos, we talked about the microscope. We talked about the simple microscope and also about the compound microscope. And in this video, we will talk about the telescope. The telescope is an instrument that helps you see things which are at a distance. Tele means far, and scope means the instrument that helps you see stuff. So, a microscope is an instrument that helps you see small things, microscope. Telescope is an instrument that helps you see things which are far. Okay. The one issue with things which are far away is this. For example, if I take this pen and I can definitely change the visual angle of this pen, right? Okay, if I keep it here at this distance, then it will make an angle in my eye. And then if I bring it closer and closer, then it's going to increase that angle. I'll have a bigger and bigger angle as I bring this pen closer and closer to my eyes. But the problem with an object which is at a far off distance is that I cannot bring it closer. For example, take the moon. I'm looking at the moon from here. Is it possible for me to bring it and then keep it at 25 centimeters? Can't. So I can't increase the angle that way. The same thing with the mountain I see there. Okay? I see that mountain. Can I bring it and keep it at say 25 centimeters and then increase the angle in the eye? I can't do that. So this range, it doesn't happen for far off objects. If the object is there, and that's the only angle I can get. I can't bring it. I can't change the visual angle at all. By moving things from one place to another, particularly when they're far away. So I can't move the moon close to my eyes. The moon is there. Can't do anything about it. The mountain is there. Can't do anything about it. So there is no maximum visual angle I can have with the naked eye for these. There is only one angle. The angle I get. I see the mountain, the top of the mountain, the bottom of the mountain, then I get, if you look at the top, then the top part is going to make an angle here. That's about it. I can't change it. So, when you talk about the visual angle without any instruments or with the naked eye, you need to understand that in the case of an object which is far away, I cannot change the visual angle. If the thing is close by, yes, it's movable, I can change the visual angle. I can't do this to a mountain. I want you to understand that. Or I can do this to the moon or a star or a planet. Can't do anything about it. So there is only one angle. So in this case, how do I make it appear bigger than it is? How can I see the more details of an object which is far away? Well, let me draw this picture. Let's say this is the moon. So this is the moon. Let me take a point here. And this is going to send light in all different directions, right? Okay, it's going to come to you, but I'm not. Let's suppose that I'm somewhere here, okay? So from this point, light goes in all different directions. And this light has to travel nearly 4 lakh kilometers to reach my eye. Okay? So here is my eye. And you see, from this point, let's look at the nature of the rays that reach me. See, these rays are almost parallel from that point. They're almost parallel, and then they reach me. So this point, okay, like the way we did for other objects was an object which was close by was this. If this is a point object, and if I have a lens like this, then you see, they come in all different angles. But if the object is far away, from that point, the light will always come parallel, because it's so far away that the angle between this ray and this ray are almost parallel. So that is this idea I'm going to use now. Okay? So for every point, we'll do the same thing. For example, if we take this point, then you see, take this ray, and this ray. You see, these two rays are almost parallel, and particularly when the distance increases, the rays will be nearly parallel. We can treat them as parallel rays because, see, they're almost parallel. I hope you understand this idea. So this won't happen, this will happen. So each point will send parallel rays. Each point here will send parallel rays. And then they will hit the eye and then converge onto the retina. Okay? Oh, this is not to scale. You can see this is not to scale. But imagine that this is the moon, and the rays are coming from a distance of 4 lakh kilometers. And the rays that hit that small eye, the pupil of your eye, will be nearly parallel. All the rays from that point will be parallel. And from every other point, you will have parallel rays coming. And then they will all form an image on the other side of the pupil, on the retina. So I want you to understand this. And if you understand this idea, then we will go ahead and do this. Let me take a lens. Again, this is the objective. Suppose I show this lens. I keep it between my eye and an object which is far away. So if we take a point, if we just take a point, and okay, let's say this is the axis. We take a point, and from that point, the rays that come will be parallel. Notice that these are not referring to two different points. They refer to the same point on the object. So they are parallel, almost parallel. So they come here. So now they hit this lens. Okay. Center. Okay. Then what will parallel rays do? Parallel rays will converge at a distance which is equal to the focal length. We've seen that. So let's suppose this is the focal length. This is the focal length. Let's say this is F. F of the objective. So let's say it's going to like that. Okay, so I want you to understand this. Okay. And let me take this line too. The ray which is going through the optical center of this lens. So all these parallel rays from that particular point are going to converge here. So this is point P. If these are rays belonging to point P, so this is also point P, all these rays will converge here. Okay, all the other rays from the point will again converge here. Look at this. Take this angle. Take this ray, for example, the ray that goes through the optical center. And look at this angle first. So this angle must be the same as the visual angle without the instrument. Why? Because if I keep my eye, let's suppose I remove this lens, and if you were to look at the object, let's suppose this is my eye, then these rays will make the same angle. This is the visual angle I get from that point. If I take a point there, then the rays will come and hit my eye like that. So this is the axis. Then you see, and this is the angle, the visual angle of the eye without the instrument too. Okay, so this is the visual angle of my eye without the instrument. When you look at the object with the naked eyes, the rays will make this angle. Simply remove the lens, put the eye there. Clearly, that's the angle. So this is the visual angle without the instrument. I want you to understand. And clearly, this will also be theta. Right? This will also be theta. This is theta, this will be theta, because this line goes to the optical center, so it will go undeflected. All these things will be deflected slightly, but this will go undeflected, go straight, because it's going to go to the optical center. So this angle must be the same as this angle. Now we got it here. And this is the point P. And then another point Q here. Okay, all these lines will be parallel to that, and that will form this will be Q. So P and then Q lines will be parallel. Right? Suppose I take this, and all the lines so they will be parallel. Okay? So that will make, let's focus on this point. So this is Q, call this Q, and call this is Q, and this is P. So P will form the image here, and Q will form the image here. Okay? So this would be the object. It's coming from. I hope this is clear to you. Okay. So, what am I going to do? Then I need to now if I look at this image, then I must be, I can probably do something to this image. I should be able to change the angle of this image. Okay? I can't do anything to this object because that angle cannot change. But look at this image. I can do something to that image. How? Let's say, let me keep a lens here. And then let's suppose I keep my eye here straight away. It's a thin lens, as usual. So this distance can be ignored. I mean, this optical center can be taken as my pupil itself. It's so close that there is no difference anyway. Now look at this. So now what can happen? So this lens, let's say this is probably the focal point of this lens. This is eyepiece. So this is the focal point of this eyepiece. So then I'm going to use this image as object for this lens. So I can take 2 points and draw the gray diagram to find where the image will be formed. Let's say this is it. And let's also suppose that I am keeping this image within the focal length. Okay, let's say like that. Okay, so this is the same as this. Okay, so suppose that this distance is FE and this is FE. Focal length of the eyepiece is it. And what would this distance be? This distance will be FO, focal length of the objective, because all these parallel lines will form an image at the focal length of this lens. And what would this be? This is actually UE, the objective distance for this lens, right? Because this is where the image is. This is UE, but this is FE. UE is less than FE. I'm keeping it like within the focal length of this. So you can understand this part. So what happens now? So this ray, we take a parallel ray, then this will go and then go through the focal length, right? Go like that. And let me take the ray which goes to the optical center of this one. This one, this one. So this is available. So clearly diverging after refraction, so it won't form a real image there, but notice it can form a virtual image on the other side. See? And this will be the virtual image on the other side. And this would be your VE. So this is UE, this is VE. Why do you want to keep it, close to this lens, like FE? Because you notice here, now this is the visual angle of the instrument, right? This is going to be theta I. Because when I see it through this, when you see the object through this instrument, you see this is the angle with which I will be looking at this image. So this is the angle it gives me. So theta I is the angle, the visual angle with the instrument, and theta is the angle without the instrument. Okay. So then my magnification will be this angle divided by this angle. So magnification is equal to theta I divided by theta. That's the magnification for me. Then what is theta I? What is theta I? Theta I is simply this divided by this one. That is PQ divided by, what is this? It's UE. Right? Tan theta I is PQ divided by UE. Tan theta is theta. For small angles, then you get this PQ by UE. That is your. Then what is theta? Well, theta, this theta is the same as this theta, which is same PQ divided by f naught, because they forming the image at the focal length, right? So theta is the same PQ divided by f naught. So what is the magnification now? The magnification now is equal to the visual angle with the instrument divided by the visual angle without the instrument. So visual angle with the instrument is this. So you get PQ divided by UE and then divided by or multiplied by f naught by PQ. So PQ and PQ will cancel. So magnification is given by f naught by U. So the magnification is f naught by UE. Okay. Now, again, you have a range of magnification, because as your UE changes, then the magnification will change. So where are you going to, what would be the boundaries? What is the maximum minimum value of the magnification? As usual, you will do a case one. So clearly, if I keep it at f naught, see, I can keep the object from Fe, right? Let's say this is, I'll call this as Fe, the focal point of E objective. I'll keep it from here, or what I mean by this, I can move the lens there, right? So that this distance could be the focal length of this objective, Fe, and some other distance which is less than Fe. Why? Because if I keep it at Fe, then I will have a certain angle. If I keep it at Fe, then I will have a certain visual angle. And if I keep it at any other place closer to the lens, then you see that angle is going to increase. The same object, suppose if instead of keeping the lens here, if I keep the lens here, so that this is going to be its focal length, then notice this is going to make an angle like this. Okay, this object is going to make an angle like this. But if I keep it here, you see it's going to make a greater angle. So this is the smallest angle, and this would be the biggest angle. Okay, the smallest angle for the smallest visual angle with the instrument, I must keep it at Fe. Meaning, if I keep it at Fe, the focal length, if this is going to serve as an object for this at focal length, then this image, where Ve, will be at infinity. The image that you have would be at infinity. Correct? So, in case 1 is when Ve is equal to infinity. It look like the image is at infinity. Okay? V is infinity. So for that, what I'm going to have? I'm going to have this. My UE in this case is going to become Fe. So this distance UE will become Fe. If U is Fe, then the image will be formed at infinity, and I have the minimum angle with the instrument. Theta will have the minimum value here. So if U is equal to Fe, then what is the magnification here? The magnification M is going to be equal to f naught by Fe. Then case 2. My V must be equal to D. Why? Because I'm going to look at the image from here. So the maximum distance, or the minimum distance, I should say, the minimum distance I can have with which I can see this object clearly is 25 centimeters for the normal line. 25 centimeters. That's what I call as d. So V is equal to d. When V is equal to d, then what would be my UE? Well, I can go ahead with the lens maker's formula, which is actually, the lens formula, which is 1 by V minus 1 by U, 1 by F. You notice that these are with the sign convention. All these are with the sign convention, right? This formula is with the sign convention. But now I am considering things without any signs. I am just taking the absolute values. That's what I am doing here. So let's see what will happen. So 1 by V. Well, when I do 1 by V, my VE will be a negative number, right? The negative number. So I will say this is equal to 1 by minus V. Because I am measuring this distance, it's a negative number. Then minus 1 by, okay, this UE. How will I measure that? My UE actually is a negative number, and that must be equal to 1 by F. But in this case, V is D, so I'll get 1 by D, 1 by minus 1 by D, and this will be plus 1 by UE is equal to 1 by F. So 1 by UE is equal to, goes there, I'll say this is 1 by FE, right? This is 1 by FE. 1 by FE plus 1 by D. So now this is with absolute numbers. Okay? FE you'll measure with absolute numbers without the sign. D without the sign again. And UE is also without the sign. That's how you consider it here. Okay. So now, so you got 1 by U is equal to this. So what is the magnification here? The magnification here is equal to F0 into 1 by UE. F0 into 1 by UE. So I'll say F0 into 1 by UE. So 1 by UE is simply 1 by FE plus 1 by D. Okay. So M let me take FE out. It's a common thing. So that will become F0 by FE into 1 plus, take FE out and then put FD. FE. Okay. So this would be the magnification for this. So the magnification of the telescope will vary from m squared F0 by FE to m squared F0 by FE into 1 plus FE by D. Okay, so this is what it is. So for the normal operations, the normal mode, then you would want the image to be formed at infinity. So for the normal mode, non-adjustment mode, then this would be the magnification, and this is going to be the maximum magnification. And see, this is, it won't vary much. I'll tell you why. You see, look at this. How can you have maximum magnification? Clearly, F0 must be a big number. Only then you can have a maximum magnification. So the focal length of your objective piece cannot be small. It has to be long, and that is why the telescopes are long, if you notice. Because only when the telescopes are long, you can have a good magnification. F0 is big. But what about FE? Fe has to be small. So this must have a big focal length and this must have a small focal length. So usually this is how it is. This is the eyepiece and this is the objective of a telescope, and this focal length is 70 centimeters. This is 70 centimeters, and this focal length is 1.25 centimeters. So this is 1.25 centimeters and this is 70 centimeters. So you'll get a good magnification, somewhere around 50 to 60 is what you'll get. That's the amount of magnification you're going to have with this. Okay. So the difference between a microscope and a telescope is this. For the microscope, we said both the objective and the eyepiece must have small focal lengths. But for a telescope, the objective must have a long focal length and the eyepiece must have a small focal length for you to have a big magnification. Okay? So you see, again, this is 1.25 or something, right? That's what I said. And this is actually this is 0.6 centimeters. That's the focal length of this. So you have 1.25 centimeters and then 0.6 centimeter as the differing focal lengths of your eyepiece. So like you can have one magnification with this eyepiece and a greater magnification with this eyepiece because it has a smaller focal length. Okay, but so typically, let's come back and look at this. 1 plus, what is this going to be? The focal length of the eyepiece. The focal length of the eyepiece, as I just told you, it could be 1 centimeter or something. And what is the distance d? That's about 25 centimeters. So that's going to be 1 by 25. Okay, and that's going to be 0.04 roughly. So it's 1.04. So it's 1.04 is almost 1. So you can take that for both image at infinity and image at d, the magnification doesn't vary much. It will be 1.04 or something, and this will be 1. There is not much of a difference between these two equations for both. Magnification doesn't change dramatically for these adjustments. I want you to understand this. And what about the tube length? So tube length would be this, right? So tube length is equal to this F0 plus UE. And usually this UE is going to be FE, we said, right? Most part. There's not much of a difference. So this is up equal to F0 plus FE. So that is going to be the tube length here. So this is important. This is important. And this is important in the sense that it doesn't make much of a difference. Okay? Because as I just told you, Fe is a small number and D is a relatively bigger number. So this term is a very small term. So there is not much of a difference between this case and that case. Okay? So I want you to understand this. The point to note here is, so this is the visual angle without the instrument. Because if I don't have this instrument and if I use my eye to see the object, this is the angle it will make. That's the point you should remember. And second point that you have to remember is that the focal length of the objective piece would be big and then the focal length of the eyepiece would be small. And the third point to remember is magnification doesn't change much between these two cases. So I can treat this to be the magnification for the most part. Okay. And the tube length of the telescope is equal to f0 plus fe approximately. So, and this is called as the refracting telescope. Why I used lenses? So this is a refracting telescope. The other type of telescopes are called as the reflecting telescopes or the Newtonians, because Newton was a person who invented these telescopes. What you've just seen is a refracting telescope, and what you're going to see is the reflecting telescope or the Neutron telescope, reflecting. We know that a convex lens and then a concave mirror behave pretty much the same way. So instead of using a convex lens, I can use a concave mirror. So I have this concave mirror. And clearly, there would be parallel rays. Let's say, if you take an object along this axis, just far away, then it will be sending parallel rays, right? Or if you take another object, point here, source, then that will be sending parallel rays like that. So this, a point will be sending parallel rays like this, and a point along the axis will be sending parallel rays like this. So then parallel rays will be coming from a far off distance. But let me just take this parallel. Let me take a point object along the axis at a far off distance. So what happens is that right here, all these rays come and hit there. Okay. Then they will be converging at the focal point. With a parallel coming from infinity, the parallel rays will converge at the focal point. So this would be focal point. Okay. Now, if I bring an eyepiece, clearly this is going to be my objective, or rather I should say it's a focal point of the mirror, and then if we bring an eyepiece here, like a lens here, right, then clearly then I should be able to improve or increase the visual angle, just as it happened in the case of the refracting telescope. Then I'll be able to see stuff very easily. So the only difference here is that instead of having a lens do this stuff, this focusing, we are using a mirror to do that. But what's the problem? The problem is that if I have the lens here, then I must be sitting here, right? And then I will be blocking the ray. Okay. Well, if it's a very, very, very big mirror, then maybe like a mirror which is as big as this building, then yeah, it's possible for me to go and sit at the center and use a lens. Okay, and actually there is an observatory in the US, and there is a reflecting telescope so big as I just told you about, and people go sit at the center, the focal point of this mirror, and observe things. So if you go and sit here, it's so big, and suppose this is your size compared to the mirror, then you see you will only be blocking this ray, right? You will be blocking only this. But all the other rays will go and hit and come back and converge here. So you'll still be able to see stuff, even though you are blocking even though you are blocking a certain part of the incoming rays. But then for this to happen, you need to have a big telescope, a reflecting telescope. Okay. So that's not very convenient, clearly. So I mean, if for a normal telescope with a size like this big telescope, okay, size like this thick, I can't go and sit inside, and obviously I will be blocking everything. So what we do here in that case is that we do this. But what we do here, I'm going to, since this would have converged here at this point. So what I'm going to do is I'm going to have a mirror like this. A mirror like this, a small mirror. A plane mirror. Okay, a plane mirror. So now the rays that fall here, see, I'll have a convenient angle. Okay. The rays that fall here, okay, will now get reflected off of this in this way. Okay. But then this is blocking. The cylinder of the telescope will be blocking. So I make a hole. I make a hole, and then I keep my eyepiece here. This will be the lens, eyepiece. So if this gets reflected like this, okay, and then you see, and after that goes like that, which I will be able to see. So you see, this will be FE, and this plus this length will be your FO. Okay, because if this mirror was not there, then would have, the line would have, all these rays would have converged here at the focal point here. Focal point is here, but now I have introduced a mirror in between, so they get reflected, and this length plus this length must be equal to this length. Okay, so this is this plus this will be the F naught. This length plus this length will be the F naught, and this will be FOA, and magnification again is F naught by FE. So this is a typical Newtonian. This is what is called the Newtonian telescope. This has a lot of advantages actually. I mean, the main advantage is that you see, light is traveling in the same medium, right? Here. So this is not subject to any the refraction effects. Like when light refracts through a prism, say different light, different colors will travel with different speeds. Okay, that we have not discussed so far. So what happens is that their refractive indices for different colors will be different for the same lens, and that is why after refraction they won't form the image at the exactly same place, and that is why after refraction you sometimes see the colored images there. Okay? The aberration, chromatic aberration, it's called as chromatic aberration. So the different colors will have different focal lengths now because the refractive indices are different. Okay, so the chromatic aberration will not happen in this case because you are not allowing light to go from one medium to another medium. Here they themselves, all of them will travel in the same medium. They get reflected, so that is one advantage. So you won't have any chromatic aberration. All the image will be formed at the same point for all of them. So that is one advantage. The other advantage is that you see, if I make a lens this big, okay, then what happens is I can support it only at the edges. Okay, I can support this lens only here. And stability, like it's not that great. Okay. I can only support here because I can't support it here. If it's a support on this side, and I'm not allowing light to pass through this. So if it's a lens, then I can support only at the periphery. But if it's a mirror, yeah, I can use the entire back side to support it. It's very easy to support this. So making a reflecting telescope is much more easier for me than making a refracting telescope. So that is why you go for this. Sometimes like it's the chromatic aberration that's kind of like that's not even present, but that's inherent here. And if you're a manufacturer of lenses, then you have to take care of that issue also. You need to ensure that this doesn't happen, and then you have to be making your glass with different materials kind of to avoid this. Manufacturing has to take care of this chromatic aberration. Otherwise, different colored lights will form different images on the other side. So you will see a colored image basically. Object will appear in blue, green, and yellow colors on the other side, and they're not together. If they're together, then it'll be white. You'll be able to see the color of the object. But then, when that doesn't happen, then you're not going to like it really. So that is automatically taken care of in this. It's taken care of. The chromatic aberration is taken care of in reflecting telescopes, and it is also very easy to support the mirror. I can use entire back side, completely cover and then support it. But here it is not so. Now it becomes delicate. I can support it only along the periphery. So then like a slight disturbance can disorient it. Here it can be very stable. So it's called as Neutron Telescope. There is clearly there is another telescope which is called as Cassegrain, which uses the same thing with a slight modification. Cassegrain telescope. C-A-S-S-E grain. Cassegrain telescope. So what happens is, in this telescope you have the same primary mirror. Okay, so this primary mirror is there as usual, and light falls on this, and like it gets reflected. The light is converging here. Okay, suppose this is a focal length. It's converging here. So what they do is that instead of a plain mirror like this, you can have another convex mirror. Okay, let's say I probably put it here. Another convex mirror like this. Here's a mirror. And what now happens is that this will reflect the light in this direction. Okay. Now you make an opening here and allow that light to pass. You can have this lens. And you must be able to see this. This is FE, and this will be parallel. So, you can use this. The advantage is that like you don't have you'll be able to see it in the same direction. Okay, but here, if in this case, if the telescope is like that, then you will be seeing it like this. Okay, because the lens will be here, so you'll be seeing it like this. But then the telescope will be pointing in the direction. You'll be seeing it like that. But in this case, you'll be able to see it like this. Okay. So that is one advantage. And by using this convex mirror, then you'll be able to reduce the size of the length of the telescope also. You can see that. When it's a plane mirror, then if it's a plane mirror, so it's a plane mirror, then it will go for longer distance, right? Converge. But if it is curved, then it will converge to short distance. So the length of the telescope can also be reduced using this. So this is called as a Cassegrain telescope, which uses a mirror, one concave mirror and then one convex mirror. But here you use one concave mirror and then one plane mirror at the center to just redirect it to the eyepiece. And here also there is an eyepiece which you will see the image through. So this is how the telescopes work. So these are three types of, actually there are basically two types of telescopes, and there are, one is a refracting telescope which uses lenses, and the other one is a reflecting telescope. And in the reflecting telescope we have seen two types. One is the Neutron Telescope like this, and the Cassegrain telescope is like this. The advantage of the reflecting telescope is that the chromatic aberration is taken care of. It doesn't happen in this case, and then supporting this telescope is the mirror is much more easier than supporting a lens in a refracting telescope. Okay. So most telescopes in the world, like the high quality, the best telescopes, if you see, like they are usually they're reflecting telescopes. And I also talked to you about another telescope which is in the US, a huge reflecting telescope where you can sit at the center of the focus of this mirror. You're actually, like, the scientist will go sit at the focus and then see stuff. So this is about telescopes. And with this lesson comes to an end. We will be starting a new lesson in the next video.